Yesterday we went a little bit on RhinoCam over the settings of the speed. That I will just do a super fast to the one, to the access profiling, whatever. And fits and speeds, we got all these speeds, and we also got some settings like the cut levels, parameters, and depth of cut. I want to emphasize the importance of these settings. One of the things that we can always adjust in the CNCs is the spindle speed. In general, we want to cast as fast as possible, like as everything. We want everything now. So in general, you try to use the spindle speed as fast as you can. But that really depends on the machine. Some machines, like they have motors, like a motor can easily range 10,000 RPMs. More or less is the average ranging of all motors, like 8,000 to 8,000 RPM in the range. Some motors, they start at 7,000 and they range up to 80,000. Some motors, they range from 80,000 to 30,000. Of course, higher RPMs on the motor means you can cut faster, but also things get a little bit more dangerous. Why? Because you need to cut faster. It means you are producing more stress on the material. More stress on the end mill can lead to the problems happening way faster. Like you can easily double the speed of cutting. If you double the speed of cutting, it means you are also not doubling, but augmenting a lot the stress on the material. That means you need to fix your material better so it doesn't fly away. And if things get loose, the machine is running faster. So an accident that happens in 2 seconds can happen in half second. And when I mean an accident is an end mill breaking, a piece flying out. It's not an accident that humans are involved. It's machine accident. Yeah.
On this machine, there is a protection around the end mill, or really it flies away.
It flies away. I have seen things hitting the walls.
Okay. Yeah.
Like depends on the part that you're cutting. This depends a lot on the geometry. But for example, a really common flyaway is you are cutting something that is something cylindrical like this, and you have a disc like this, look like a joystick, hockey disc. These guys, they love to fly away. Cylindrical parts around like smaller than 7 centimeter diameter, they usually get into the spindle, and because they're round, they flip over and they just fly. So especially with cylindrical objects, I'm especially careful because they usually tend to fly away. What we do for this in general is we put more tabs, or we either use a pocketing to eat all the material, so we destroy it. It takes more time, but it's slightly safer. Said that, not all the materials cut at the same speed. Like the materials have the chip loads that are the range of cutting. Different materials have different chip loads. And for example, this is a super standard, like super broad range of chip loads for a standard end mills, like to flute, up cutters. So for example, the chip load of aluminum is 0.8 in the lower range, or 0.13. Meanwhile, for example, for wood, it's almost triple. That means triple the chip load it's not straight triple the speed, but it's way easier to double the speed on the mid range. So that means aluminum cuts way slower than MDF. That's a little bit clear, but it's way slower. That means you cannot go faster. At the same time that you cannot go faster, you need to reduce also your spindle speed. So actually, to cut aluminum, you always, in general, unless you are doing fast milling, you want to go on the lower side of the RPMs. Meanwhile, for example, on foams, you also want, with wax is a material that if it hits, melts. The wax for CNC milling is wax mixed with plastic. Is natural beeswax mixed with HDPE or low LDPE type of plastic. So it increases the melting temperature. Instead of being 60 degrees, it's around like 120, 150, depends on the type of milling wax that you're using. Examples of milling wax, some of them here. So, for example, these are two pieces of wax. You see there are different colors because the color code on the material tells you the hardness of the material. So, for example, this is meal wax. I don't know if you can see well. You can get really thin and nice finished cuts. For milling wax, in general, you want to run fast on the X and Y, like on the what is called feed rate or horizontal speed, but you want to go slow on the RPM. So you want to eat a lot of material, but with a slow RPM. So you want to have big chips and almost fill the whole flute of the end mill. When you're cutting, I don't know if you can see it. Well, maybe a background. Let's improve the setup. So when you are cutting, where is the camera? When you're cutting, this is super clear. You have a big hole inside the end mill. This is one flute is really big. So you want to have the flute completely filled. It means like fill the whole spoon of the end mill. So actually you get a lot of heat exchange, and by so the material doesn't heat. So in that case, you also want to go to the lower RPM. What I'm saying that, for example, the speed that we are using, this CNC machine that we have is quite sturdy, and this motor is quite powerful. It's 2.2 kilowatts, like more or less 2 horsepower, and rotates 18,000 to 24,000 RPM. 24,000 starts to become quite fast on the RPM. That means if you use a two flute end mills or higher flute end mills, you need to even go faster. So two flute end mill plus really high RPMs. Let's take notes. Paint. If we have an equation where we have the RPM versus number of flutes, this is the speed. Oh, sorry. Equal x. This is a constant, or constant of, for example, 1. If this number is high, this number is high, to get the same balance, this number needs to be high. So you start to have a problem of fitting. That is, your material, you need to cut fast, yes or yes. And by so, you need to fix your material well. And not all the cuts can be fast because you have a constraint. One thing is cutting 1 meter fast. Another thing is cutting a design that is like this fast. Some designs cannot be cut fast just because of the geometry. So there we have a problem. How we fix this? For example, in the other building, we have machine the same size, but the RPM of the, let's say, P102, this is this building, the machine ranges from 18,000 to 24,000. In the other building, the machine is the same size, actually it's the same spindle, also 2 kilowatts. And the RPM of that machine ranges from, I think the lower one is 7,000 to 80,000. That's almost double the speed of the cutting. That's good because you can cut really fast in here, but you need to know what you're doing. When things become fast, everything becomes way more sensible, and at the same time, you cannot make mistakes because this number range way faster. So how we solve this? By reducing the number of flutes to the lowest as possible. That means in here, for example, we always try to use one flute, 2 flutes at a maximum. That is already good because 1 or 2 flutes are really forgiving end mills. They have a really wide range of working space. It means you can accommodate a lower speed and it's not really sensible, or you accommodate a higher speed and make the end mill work a little bit harder and still will work well. Maybe it's overheating a little bit, yes, but it's not that. It's a little bit forgiving. The 1 flute end mill. When you go to 4 flute end mill, they really become really fast, hot. Why? Because you have really small space for the chips, and that means you need to cut a lot with each one of the flutes, and have the flute space always filled. What is the lower limit, the limit rate you can use? If you are not confident or you don't know exactly what you're doing, go to always the lower one. Let's say the lower one in this machine. If I go to any machine, I will start with a mid-range that is 14,000 to 18,000. That's like really average range of kind of any standard CNC. But I have found CNC machines that get range up to 40,000 RPMs. Those guys are really fast. And what usually happens is that is with router motors. Router motors, yesterday I explained, I don't know if you remember, that we have two type of, let's move this. Yes, that we have two type of motors. Spindles, the one that you can control the speed, they work on horsepower. These ones, you can usually have lower RPM. Routers in general, like they're weaker and they work on really high RPM. So in general with router, you are always undercutting because you are working with really high RPM, you are never to fill the end mill with enough flutes, and you always consider that you will overheat a little bit. So that's why it's better in also one of the reasons why it's better to run with a spindle. Why this is important? Because in the router, you don't control the RPM on the computer. It's not a number that you set up. It's basically you have a potentiometer, a knob, like the same as your hi-fi, and you do it by here. So it's not as scientific as you want to sell it. It's about more about technique and having a little bit of experience on tweaking out the motor. Let's go. Yes.
When you were saying that if we go with a faster speed, we need to secure better the material.
Yes.
It's only like the screening outside the material, or if we are, for example, creating a circle, having larger parts, so the circle doesn't fly away.
If you don't fix the material, it does this, literally, like, but at really high speed. So you need to fix everything.
Edu, we can't see you, so if you can remove the background, because we don't know what this is.
Sorry, like basically I just throw like a tape to the wall.
Okay, beautiful, thanks.
Yeah, the background. Hello. So it's quite important to fix all your materials. So actually, in general, here we try to cut slower to be safe, like go with end mills that they are 1 flute, the lower RPM, so we don't need to cut really fast. That's why, for example, the average speed that we use for cutting most of the woods, like plywoods, is like 5,000 millimeters per minute. If you want to pump the machine, like when I have to make furniture or I need to make 20 benches, I know what I'm doing. I fix things well. I'm cutting at 20,000 RPM using 3 flutes. I'm cutting at 15,000 RPM, millimeters per minute. It means 3 times faster. Yes, but the machine starts screaming like, whoa! It cuts hard. Like things get messed up really fast. Like basically you have no time of reaction. If you cut at 5,000 millimeters per minute and you hear like a weird sound like, you have like 2 seconds to touch the emergency button and stop. At 15,000, basically you don't have the time. The mill just slaps. Usually, like it's no time of reaction. The other one is time of reaction. Some materials, on the other hand, they don't want to be cut slow, and that's more technical. For example, alugubond, even if it's aluminum, because we have home core, you want to cut really fast. You need to jump to 9,000 millimeters per minute, yes or yes. So in that case, you cannot play with the range. It's the range you have, and you need to deal with. So in that case, you want to fixate your material properly. In that case, we use double-side tape and screws to have double fitting. We have the step down. That, as I said before, is how much material we eat at a time. And yesterday I showed you a little bit lost, so I made few drawings. So if we have this piece of material that in general, this is slightly smaller. let me draw a new one. This is our end mill. Let's put this on the back. Arrange, send to back. And let's change the color of this, or just a background. Why is not coloring? Don't worry, let's fix it. Arrange, send, bring to back. Okay, so we will have our end mill. We don't want to cut in one cut. You want to cut a little bit, do one pass, let's say one step at that layer height, and then move down and do another step at that layer height, and then move down and move another step in the layer height, and then move down, and like that, so on, until you cut your all material. You move steps down. That is called the step down range. The step down range is something really variable, the same as the speed. So if you want to use the equation, like the equation that we were using before, this equation only works if you cut half the diameter of the end mill. So half the diameter of the end mill. So the rule is, if you want to use this chip load equation, the cut depth or step down is easy. It's half the end mill. So if you cut 6 millimeter, you cut down with 3 millimeter step down or cut depth. It's really easy. Usually it's not exactly half, but it's like estimate. You can go a little bit down, a little bit up. In general, it's better to go slightly down. So it's like 40%. So if you have a 6 millimeter end mill, you cut at 2.5, 2.8, 3. You can go a little bit up, 3.2. Why? If you go a little bit up, what you can do is you are cutting more material. That means you have more chip load. That means you can reduce a little bit the speed. It's a balance. It's the total amount of food that each flute is eating. You can increase it or reduce it by changing the speed, changing the RPM, or changing the amount of material that you're eating down. So for example, compression cutters. They are difficult to use. Background. Compression cutters. I don't know if you see it really well, but has double geometry. You see that on this side. Oh, yeah, now better. And has like a weird geometry. It's not exactly straight. It's changing the direction of the flute. These guys, you want to cut your material at once. You enter the material at once. Why? Because they change the geometry in the middle of your material. If you don't change the geometry in the middle of the material, it really doesn't make a difference to use this and what happens if you are eating all that amount of material at once. You need to reduce a lot the speed to don't augment the chip load and increase also a lot the RPM. That's why they are difficult to tweak and where the chip load doesn't work anymore, these equations. So it's a little knowledge. Then we have the step over. That is a value that you will not use a lot now. You will use in 3D milling. But let's see, this is the end mill. Sorry, yeah, thank you. This is the end mill, and you want to cut all this material. It means raster all the material, destroy it. This is about how much we move on the side. I will change the color of this end mill. So we have made.
Edu, are you sharing the screen?
I'm sharing now. So if you want to cut all this material, the end mill is going to follow this path, this line. Sorry. It's going to make this line. And then it's going to come back and do an offset of the line. These ones are automatically generated. This is called what is called toolpath. And it's going to make the next offset. What is the amount of offset or the total amount of movement that we do on the side is called a step over. How much you move on the side. The same as we have step downs, we have step over. It's a really similar, it's the same thing, but instead of moving in the Z, it's on the X and Y. The offset on the X and Y. The step over, they also have a range to make it work with the equation that is half of the end diameter. That, as everything, is not a golden rule. It's always better to go at 40%. Why? Imagine that you are cutting your material with this mill. Drawing this is a little bit difficult. I will try to do my best. So this is the material that we are eating with the end mill, arranged into front. And right now we are in the center axis, no, of the end mill. Let's draw with another color, green. So we are in the center axis of the end mill. That means we are cutting with knives all this area. We are moving to the top. What is happening here? Like we are in the middle of the other, almost the other side of the circle. If you look this at a small scale, like with a really high-speed camera and with a microscope, the end mill is micro vibrating on each flute. It's making jumps. This effect, it will happen yes or yes. But if it happens too much, we will cut making jumps between each other. And that is called, it's a sound that you can hear sometimes, and it's not a woo clean, it's like woo, a little bit of like, oh, I don't know how to explain that sound. Growling mid-level sound, that is called shattering. That is when the end mill, basically, I need to point the camera on the table. You have the end mill cutting. This is the end mill cutting vertically. When we cut on the side and we make too much force, sorry, the opposite, the end mill breaks. I'm holding it down, but you see the end mill is bending a little bit. This usually tends to happen with really long and thin end mills. So in general, we say that bigger is better. Yes, bigger in diameter, not in length. You always want to have the shortest length as possible, so the end mill doesn't bend. And this happens at really high speed. It's impossible to see on the eye. The only way to see it is if you have a high-speed camera. You can see on the side of the cut that, I don't know if we have an example here, because we always, obviously, we try to avoid it. But I have a picture I found yesterday that is really exaggerated. CNC speaker passive. CNC open vertical. No. Is picnic table. Camera slide. For example, this is cutting HDPE. The cut is not the best, and we can see a little bit on the edges. Okay, you see these micro lines? These are two reasons because having these lines. First is using a straight cutter. A straight cutter usually tends to give this cut because we are cutting once. So a straight cutter tends to shatter way more than other end mills. Doesn't get a smooth finish sanding cut. And this is micro shattering. This could become way worse, and you actually can see the jumps. Usually, you see the jumps. The noise is also really huge in that sense. But you always want to have avoid that the mill bends a little bit and shatters. So say that when I'm saying that So what we want to do is never cut at half. We just want to help the end mill to cut the best as possible. So we try to cut at 40%. So the end mill is beyond the, more or less, if you want to center, like this is not 40%, but you get the idea. Ooh. You get the idea belong this threshold. That is, you leave a little bit on the exactly the front side on the end mill, so you cut a little bit on the side, so there's already a tilt that helps the end mill to attack the material. So we always try to cut at 40% on the step over. Both. In climb is more exaggerated, this. Obviously, because in climb we are attacking directly. In conventional, we are attacking on the soft side, so it's not that extended. Yes, we have more material. Saying that, 40%. In case of foam, you can cut up to 80%. It's foam. It's super soft. We don't care. Like, it cuts well in every direction. You can save time depending on the material and how you attack the material. For example, this, it's a chart of how actually the chip load changes depends on the diameter of the end mill and the RPM you are using. You see, it's a really non-linear. And this is why we have the chip load equation, because actually helps a lot to get to this range. If you are working with the full size of the end mill and not cutting half of it, this equation depends on the material, but might be as something like this. And you only have a really sweet spot of working without damaging either the end mill and getting a versus a clean cut. Even so, I know more or less, I have a lot of hours of CNC cut experience. Even so, I always try to stay in the chip load equation. It's like, unless I'm really in a hurry, I need to cut, I need to push things a little bit further, etc. It's a good, safe work way, and you always stay in the safe side, and no problems will happen in general. What else? Yesterday, I don't know if it was clear. For example, the in cut, we have this vector. We can proceed to have an in cut, an out cut, and an on cut. So if you cut outside, it's because you want the inner part. If you cut inside, it's because you want the outer part. It means you want to have the window frame. If you want on cut, it's because on your design, you're already accounting for the end mill diameter. If you know that this is a 6 millimeter, you know that you are eating 3 in this direction and 3 in the other direction. So you can design, if you want actually a 90 millimeter part, well, this is not 90. Let's say I'm using a 10 millimeter end mill, okay? This is 5 and this is 5. If you want a 90 millimeter piece, you can produce an offset of 5 and 5 because you are cutting 5 all around your object, and produce automatically the cut on the line. You cut on the line. It's important to, really important to understand this. Why? If you have a square, it's really easy. This is super thin. If you have a square, it's really easy to know what is inside and what is outside, no? How we know what is inside and what is outside in a straight line, open line? There is no way to know it. So actually, you can only choose between outside and inside cut in closed vectors. In open vectors, you cannot choose it. So it's something that you need to be accounting for. You could have easily a shape like this, but you see the vector is not closed at any point. In this case, we cannot make outside or inside cut. We can only make on cut because the vector is not closed. If you want to actually do it outside or inside, the vector should be closed. An Illustrator is not the best to show you this because it doesn't close well the vector. But join, yeah, join. So now this polygon could be cut outside or inside. Really important to know that. It's something that you can take into account. And I will show you with a simple example. Cheap chair. Okay, this chair, this is the sitting area. It comes from the side, like is the space you have on the side. And you can see here the cut. This top, you want the inner part. It means you want to cut outside. But in this case, you want to also the frame length. You want to cut inside. If you account already for the material that you are eating with your end mill, this depends a lot on the tool you are using. You can cut, uncut, and produce 2 cuts in one. You can save a lot of time because you can merge 2 cuts into one. The same happens in the laser cut. You can cut with just one line. You can cut with the left part and the right part. You don't need to cut them twice. And it's quite important in the CNC. You don't want to overcome things that you already cut it. Why? If, let's say, we have cut this, and then we come back, and then it gets introduced into here, what is happening? The material has moved a little bit, just a little bit, enough to hit on the end mill at really high speed. Again, you will damage all the side of your cut if you already cut in the same spot. You can make it happen. Actually, you can see here, the line is a little bit offset. Why? So I never leave enough space of 6 millimeters. This was cut in a 6 millimeter end mill. I just make a little offset so it never touches again the same area, just in case it doesn't damage the design. You can make really thin fits, but you always need a little bit of material. Let's go a little bit on the what is since explanation. Why? You remember the difference between a down cutter and up cutter? Up cutter pushes the material up. What is this? Okay. Drawing text. Okay. It's pushing the material up. That one of the reasons why we cannot use. The screen went out. Why? Let's see. My computer is freezing or doing what? Okay, connect. Itachi, connecting the device. Sorry, connection problems. Okay. So, clear all drawings. So the up cut is pushing the material up. In this case, if you are making just a hole, you can do it. What happened with the end mill that is pushing the material down? There is no space to put the leftover material. What happened when you rotate a wood stick against another wood stick manually? Fire. It's exactly the same in the end mill, but instead of a wood stick, it's a metal stick. So it's even worse. So basically it's that. And wood is a material that can get compressed. You compress the material while cutting at really small scale, or like foams or wax. Wax melts a little bit, but aluminum and metals, they don't compress at all. Like they compress, but really small percentage. That means if there's no space to go, basically you create an explosion. Like I never had the guts to try it, but it's something that is like kind of physics 101. You should not do it. This is about 3D milling. Yeah, how much space you leave on your parts. When we cut, we are making an outside cut, and this is the tab we want to leave to hold the parts. This tab might change, depends on the material you are using. You want them bigger or smaller, depends on the material you're using. But if you don't leave enough space between these two cuts, they say we have cut this part and we have cut this part. If these two parts were close enough, we will not have this material. So that means your tab is going nowhere, attaching to maybe, if you have luck, another tab. So you always need to leave enough material so the tab can attach to something that something or leftover piece of material is not going to be cut by something else. It's quite important to leave this one. I usually follow the rule of 1 centimeter. 1 centimeter more or less holds well, unless you are cutting something that is super. You have this is your piece of wood, and you are cutting shapes like this. If you have something that is only 1 centimeter, that at this scale more or less it will be something like this. How strong is a 1 centimeter piece of wood that measures 1 meter? Nothing. It just vibrates. When you're cutting, actually it will vibrate, and you will hear the sound like on the machine because it's the piece of wood flapping. When you're cutting the part next to it, when you have cutted this one, so this side is already loose, and then you cut this side, so the piece of wood is not attached to anything, we vibrate a lot. In this case, you don't want to use, for example, 10 millimeters here. You want to use like 30 or 40. Depends also on the geometry you're cutting. For example, if it's a full plank, I will leave 30, 40 easily. If it's a really small area, maybe if my design is something like this, maybe we can reduce this margin to 5. We can make them thinner, so we save a little bit of material. Everything depends on geometry, also on speeds of cutting and material you're cutting. I know it's annoying, like that's the annoying part of the CNC. Everything is variable, a lot. You have a really safe margin area that you can work it with no problem. 5, 10, like 10 millimeters, 20 millimeters. Yeah, you waste material, yeah, but we stay in the safe side. We can cut slower at slower RPMs. Yes, we give more room to play with the margin. Slower RPM, slower speed means we have less strength on the material. That means even if we leave a small piece of wood that is weak, we are not pushing it too much. That means it will not vibrate a lot. If you leave the same material but you're cutting at triple the speed, it will vibrate a lot because all the machine is vibrating. You touch the machine, it vibrates, like actually vibrating. That's one of the reasons why CNCs, they weight a lot, because they need to counteract that the vibration produced, they don't move. Actually, just for curiosity, CNC machining center, more or less like 30, 40, let's see. No, that's the CNC machining center. Let me remember the name. Because more or less I know the estimates of weight because of the size. Okay, something like this. This is a small, actually the working area of this is really small. It's like 30 by 30 by 30 in general. The machine is huge because first it has like water cooling, so it needs like recirculation of fluids, has a stronger motor. Usually it's like there are 4 or 5 axis machine. This is just the control box with all the electronic that is isolated. This machine usually they have like a marble piece on the bottom of the machine. Just to make it heavy so it doesn't move. So also the structure, like they have a huge metal frames that are like ultra reinforced. So actually the machine doesn't bend even a little bit when cutting. Actually these machines, they are not that huge. It's like a closet. They weigh the same as this machine. Like these are arranged like 600 kilos easy. It's like a full table. It's really the same technique, like mass to create inertia and make the machine stable. This one, we lift it up, like we bring it again 2 years ago, more or less, and there was the truck coming up here and the two forklifts lifting up the machine. Was heavy. Like I think this machine is also 600 kilos around. It doesn't get to 1 ton. And actually, like they are overrated on the profiles to make them stronger and also more heavy. The foundations where you put the machine is also important. For example, if you put the machine, a 600 machine, in a building that is made out of wood, the wood also vibrates, the building vibrates. Like you can feel it. For example, in the last lab that I use, usually the mainly machines are like in the basements, so they are touching the floor, so they're more stable. The last one, I was on a 5th floor, but the 5th floor where the machine was inside was a safe bank. Was the old safe of a bank. Actually, was like 1 meter concrete block all around the safe to make it stable. Okay, let's don't get too messy about this. So we went down. Climb and conventional. The best drawing is this. In general, always try to approach with climb, with, let's say, mid-range harness materials. You can cut, I can cut aluminum with climb, and I cut aluminum with conventional. Almost no different in the outcome, big one. But for example, in the small SRM machine, that's the one they use for milling PCBs, I was cutting aluminum. I know that the motor of that machine is not strong. So I was cutting first at really slow speed, and then I automatically start to cut in conventional, not in climb, because I know the motor will have problems to cut because it's a weak motor. If you trust in your machine and you think it's powerful or not, always start with climb. Ideally, you should do the tests in climb and conventional to see which one gets better, especially with weak materials. For example, with foam, foam is a material that gets compressed. It means when we start cutting all this area, the material gets micro compressed like this. So that means when you attack with a cutting knife, the flute of the end mill, it never gets a sharp and smooth area of material to cut because it's micro vibrating. Actually, when you cut foam, you get in general really bad results. This, like, you get awful results cutting in climb and super nice results cutting in conventional. For example, this is a cut made in awful cut made in climb. If you have made this in conventional, you will get, for example, the quality of the map that you had see there. This is foam. The whole Barcelona map there is foam, cut it, and it's cut in conventional. And this you can choose the best end mill for just an end mill for foam. It doesn't matter. If you cut in climb, you will get a full result. You cut with conventional, you will get awesome results. As easy as just changing the technique. And how does this translate into the machine? Is with the end mill always rotate on most of the machines clockwise. If your machine doesn't rotate clockwise, you need to change everything. Conventional is climb and climb is conventional. It's a little bit annoying, but and also down cutters are up cutters and down cutters are up cutters. So, but in general, most of the machines they work clockwise. So what happens is you basically, if you have a square like this, it's not the same cutting clockwise. Sorry, wrong color. Cutting clockwise or cutting counterclockwise. Actually, cutting climb is cutting counterclockwise. Cutting conventional is going clockwise on the cuts around the edges. The tool is the same. Actually, it's something that I don't like about RhinoCam is it doesn't say climb, well, it says climb conventional, but on the next to it, it says down cut, up cut. That is like really confusing. Like it's actually changes depends on the mill, but it's not like that. Like it doesn't, it's not that clear. No, the motor still rotates. The motor rotates always clockwise. It's the how you move the whole machine around your object. The motor always rotates clockwise. That, and there is one big reason. Let's show it in a picture here. I think it's easier. Is the collet of your machine. Here, this, that is the collet chuck or the collet nut, basically is a nut, tightens counterclockwise. So if you rotate clockwise, even if you didn't tight well enough the nut, it will self-lock. If your motor rotates the opposite, it will tend to unlock. And this is something that you don't want to happen. That's why most of the machines rotate clockwise. So they tighten the nut on their own rotation. Just in case. Even so, you should never cut with a non-tightened collet nut. Talking about, we also went yesterday a little bit on this, the collet ones. So for example, this is a collet, and you can see, maybe you don't see it really well, but my hand. In here, trust me, there are some numbers. Maybe we can see a little bit. Yeah, we have some numbers. They state first the exterior part. These guys, they are mid, big, small, depends on the motor you have. Smaller motors have this part in the small. Smaller motors have this part in really small. This one is a standard one, is a ER25 size. Is more or less the standard size between 1 kilowatt to 3 kilowatt motor. And they tell you more or less the maximum size of end mill that you can take, basically on the whole. You cannot put end mills bigger than the collet size. So a ER25 can fit a maximum of 25 end mills. How to know if you are choosing the correctly? Also, the collet chucks have, this one is really wasted, but has some numbers, and they state the inner diameter. The inner diameter, you need to match it with the end mill. For example, here I have I think this is a 12 millimeters. This is a 12 millimeter end mill, and this is a 12 millimeter chuck. If you put inside, it fits exactly. And actually, I'm not pressing it, but it doesn't fall. If it falls, it means your collet will probably need to be replaced. It's a little bit wasted. And you have collet chucks of all the different sizes. You have collets. Some of them, they state two numbers. For example, this is a 3/4. If you can accommodate 4 or 3, I'm not especially fan of like the multiple ones because they don't hold really well the 3 millimeters and they hold too much the 4 millimeters. I think it's better to, these guys are more or less cheap. They are 20 euros, 50 in the worst case scenario. It's better to have one for each specific measure.
What's the issue if you hold one too strong?
You can damage a little bit the thread on the motor while tightening because it's a little bit too much pressed. Like it doesn't come as smooth, and the thread of the motor are expensive. So actually, trying to save like 20 euros versus a like 3K motor or 5K motor really doesn't make any sense. Some end mills like this one. Let's try to get close to the camera. Like this one, for example, this is I'm rotating clockwise what this end mill is. It's a question. This is a down cutter. Down cutter, one flute. We can see usually the flutes are easier to see on the top. We only have one cutting knife, one big cutting knife in this case. Also, it's a special type of one flute. This is a one flute off flute. You see these little spaces here on the back? This is called off fluting. Actually, this is taking the leftover chips and pushing them on the back to the top. It's like helping to dissipate the material out. Off flutes are good in general really good for plastics. When you cut with plastic, you always try to have an off flute end mill. Let's see, we have non-off flute end mills around here. Like I think most of the flutes we have here are off flute. This is not. No. This is not exactly a. Oops. This. Focus. This, for example, is a two flute. Two flute round point. This is for making finishing or three-dimensional cuts. But you can see that we have one flute here and one flute on the other side. But in the space on the back of the flute, there is smooth. This is not a flute. In general, like round cutters don't have a flute. This is a weird example, but if it was a flute, we will see, instead of a shiny surface, we will see the little engraved marks that are like mini flutes. This is because you can find off flutes, non-off flutes, and in the off fluting world, you can find big off flutes and small off flutes. In general, big off flutes are better for like woodsy materials, and smaller off flutes are better for smoother finishing and plastics. The camera is tilted. Okay, let's keep sharing the screen a little bit. Types of joinery. Importance of G-codes. You will see that usually in general CNC machines, they always tend to show you what is happening in the code. When you saw yesterday that when we exported the machine code, it automatically opens Notepad or whatever Atom you have and shows you the G-code. Because it's quite important to know what is happening. Like most of the decent CNCs, or like more or less professional CNCs, the interface of the machine is not just a gamepad. It's a gamepad and it's showing you how it's loading each line of code. So actually, if something bad happens or you want to stop the machine, you can stop in this line, know exactly what is happening, and maybe skip another line or move back 3 lines. So you can stop and roll back on the code. And it's important, and from now on, you will need to start a little bit familiar with basic commands of G-code. Of course, it's not mandatory, but it's really recommended. So for example, if the machine stops suddenly, for no reason, it will show you exactly in which line or what exactly happened. Or let's say you go for the restroom, someone stops the machine. Nobody should touch the machine that you're using, but stops the machine and closes the file. You can always come back and start exactly in the same point on the line that you were working on. So we have first command, that is G20, that is working in inches or working in millimeters. This depends on the firmware of the machine and where are you from in the world. We have G0 command, that is make a fast movement. G0 command, in general, you don't state a speed. It uses the by defect of the machine. By the defect of the machine, usually as what is called like air traveling speed, and it's a quite fast movement. And then we have the G1, and that like are the commands to go to some certain position at a specific speed that you have state. Let's see a little bit the codes that we did yesterday. This, for example, this one. So this one is sorry, G90. It's like G90. Sorry, I don't remember all the codes always. G90 is absolute positioning. G90 G code. Yeah, absolute positioning of the machine. It means use the absolute coordinates of the machine and not use a offsetted one. You can use the standard of the machine. M7 is weight, and the weight in some machines you need to state the time. Usually it's M7T500, wait 500 milliseconds. Some machines they don't need to state, they just pause for 2 seconds or 1. It's predefined on the software. M8 is switch on, switch off the spindle, just in case, if by defect. As far as I remember, M8 is switch off the spindle. Let's just check it. The one to make to turn out any output. Sorry, actually it's the opposite. Turn not cooling in case you have it. T1 is select tool 1. Some machines that have automatic tool change, and you have predefined T1, T2, T3, T4, T6, T7, and they will automatically know which tool they need to grab. If you don't have an automatic tool change, you can just inherit T1, that is, use the one that is already in the machine. S80,000 is set up the speed for the motor, that is the command M8 at 80,000 RPMs. If you want to change the RPMs after you export the file, or you are working on the machine and you don't want to come to the computer and make a new file, you can just change this to the speed of the RPMs. M3, as you can see, I don't remember all the commands, but I know I'm familiar that M commands are to activate or deactivate things, and G commands are for movements. It's confirmed that the mill is on. G0 is move fast 20 millimeters in the Z. G0, make a vertical. G0 is do a fast movement. We don't tell the machine how fast. It will take the defect values of the machine, the one that are saving in the memory. After we move up, it will go to X178, Y223. It will do a fast movement in the air, and then it will go at a certain speed. This is G1. It's a command that we are not doing what is called air traveling. We are not moving in the air. We are activating. It means we are attacking the material or approaching the material. Maybe we are not still touching the material, but we are going to go to cut. It means move in the same position. Actually, we just said move to Z minus 1.8 at 4,000 millimeters per minute. And then we are making these small movements. You see the position is almost not changing until here. And what we can see on the Z. You remember that yesterday we explained that we always need to enter in a ramp, in a slide. What is a slide? A vertical and an XY movement mixed. We can clearly see from this line to this line, the position has almost changed just 1 millimeter on the X, 1 millimeter on the Y, but from 0 to 3. So this is the ramp, and we are doing the ramp at 4,000 speed. We have reached the full step down, that is half the end diameter, minus 3. It means we are already at that level. So now we are approaching the cut. We are starting a cut. And you see, this is not a G1. This is a G3 or G2. This G3 because it's a climb. It means a counterclockwise arc. G3 is for arcs on to the left. G2 is to arcs to the right. Basically, it's a movement calculated between a center and a radius. That's why we have the center of rotation and the arc radius. See, I will show you this 1 second. G2. So, yes. This is to make arcs and how they calculate the commands. It's a little bit confusing, actually. Like we have the start point, the end point, and the center point to calculate. In general, like I don't like to work with G2 and 3C commands. I prefer to work only with G1 and make polygonization. But they are optimized way to cut with less amount of G-code lines, and actually is in general is better for the machine because it cuts slightly faster and keeps better the speeds. But that's why we have post processors, so we don't need to mess up with these kind of things. But it's important to know that a G3 command is an arc command of a G-code. Then we have another arc, and then we are still cutting in a straight line, and then we have another turn, and then we have another straight line, like so on, so on, so on, so on, so on, so on for like 5,000 lines. I think has this file. It's important to know a little bit, at least the basic commands. So when you load a file is, or want to check that your file is okay, if you just check the header of the file. That is the first 10 lines of the code. That is the basic settings. For example, if you're cutting here and you see G20, something is clearly wrong. Your file is in inches and your design is supposed to be in millimeters. you see G53 instead of G90 is you are using relative coordinates, not absolute coordinates. So maybe the origin you didn't set up the machine properly. Don't worry, this you will get used to, and we have just one of the maker clubs is going to be dedicated for that, and we use that machine. That is unproof, and if you put the wrong commands, it will just clack, and it's weak. Let's say we have made it so you can move it by hand and touch it and experiment with it. Terminology when producing CAM files or tool pathings is we have a roughening, is what the name states. It's a rough cut. It's a fast, not super clean cut. In general, this terminology is used only for 3-dimensional milling, not 2D milling. So we will not see this week. It's not exactly like that because you can also do rough cuts and finished cuts in 2D milling, but it's slightly different. I will explain that in a while. We have finished cut, like the last cut, and it's like a sanding cut, is the one that you get a smooth and clear finish. We have profiling. Profiling is cutting in, out, or on a line. It's following a vector. Could be inside the vector, outside the vector, or on the vector. We have a step over, the movement on the side of the end mill, on the X and Y plane. We have a step down, the amount of movement on the Z. We have the feed, height flow limiting controls, that is cutting speed or horizontal speed. We have plunge, think about plunging in the swimming pool, like you go inside, so it's Z movement. When we will go on 3-dimensional cutting, and feed rate, they will need to match. Why? Because if you want to move 3-dimensional really fast, you need to coordinate 2 different speeds, horizontals and verticals. In 2D cut, this one could be completely different. And actually, for example, for cutting aluminum, you want to plunge really, really slow, be faster on the X and Y. LED engage, this depends a lot on the software, depends on the machine. Also, it could be activate, enable something. Pocketing is destroying all the material inside. Like facing is the same terminology for that's pocketing, but when you cut all the material. It means, for example, you have a 20-millimeter board and you want to make it 18. So that is a pocketing, but it's called also facing because you do all the face of the material. And a lot of the softwares, like the software to do tool pathings, they don't call material thickness, they say stock thickness. Good tips. Vectors in general, I always try to work with DXF or standard vector files and always with polylines, nothing special, like no rust, no hatchet, no anything. Be really careful with duplicate lines. Don't have duplicate lines, it's really important. And a lot of the softwares allows you to put PNGs to do bitmaps and engravings. For example, Aspire, PNG, no, let's go bitmap. This is a software that is usually for woodworking, for making 3-dimensional engravings. So, for example, this, super high quality. These really complex designs are not vectors. They could be a 3D file also, but in general, you do this with an image. So you work with the gradients between black and white, and you establish black being the top or the white, depends on the software, being white, what is the maximum depth that you want to reach. You don't have too much control over the depth and how deep is each area, but you get the 3-dimensional part. This is for not accurate cuts. If you want to have a really accurate control over the whole geometry, you do a 3D file. But that also implies like more technical side. So for example, this kind of engravings, they can easily be done with just an image. And the software does most of the magic right now. It's super nice. or these kind of things, like depends what you want to do. So if you want, let's go again over this. We can close.
So if you have a small detail that requires a small tool, but on a big survey that maybe wants to work fast.
Good question. Let's do it. Let's do it. I will show you an example of how to do it. Need to close a few things. My computer always tends to explode. For example, this is a huge CNC. Like this is not exactly a CNC, it's like a special machine, but to make both holes, but it's like that. So basically it's a hard frame and this is all foam that you mill it to, so you can cut fast to actually make the mold of a frame of a boat. Be really careful. This is a really common mistake, especially when you are working with really thin materials. This is the dust collector or the dust cover that you say before. This actually prevents the machine to actually make the parts fly away. Some machines have this part made in light plastic. Some of them, they are like really sturdy. And when you're cutting, you don't see the cutting part. I might have a picture. Of a CNC like that. Yes, for example, you see this machine. This is a metal cover that hides the motor with a like 20-centimeter margin and has some brushes around. Not only helps to keep all the, you see how clean this lap is? It's not because it's not being used. It's because actually it helps a lot to keep all the dust controlled in that area. You have a bad point also that you don't see when you're cutting. Like if you are not experienced, playing the magic button and hope that everything is happening inside the box that is moving with the motor nicely, you need to recognize the sounds easily. You need to know that your file is well done. So it's a little bit less forgiving to mistakes, because if you have the cover clear and transparent, you can really see that something is not happening as you want, or you didn't set up the file properly and you can stop it. In the other ones, you need to wait that it finishes, especially for small parts, to move the machine away. So actually you can see it. Exactly. You'd also, those machines are meant to use like big flat parts with not three-dimensional parts. So for example, some of the machines that we use, for example, this CNC step basin or like these shop bots, they have this point and they have the motor slightly down. So actually you can reach higher three-dimensional movements without collisions. If you have a big area around your motor, you cannot make three-dimensional movements, or you need to disassemble the part to actually be able to make three-dimensional movements. This machine, you can see the bridge is small. Also, this machine is not especially meant to do a lot of three-dimensional movements, because this is a machine for production. This is a machine for deep production. It's like it has all its vacuum bed. It means you put your bed, you attach. In 2 seconds, you have fixed your material. Second, the bridge is small. That means the machine is even sturdier because there is less cantilever on the machine. And they have this to collect the dust and keep every area clean. Is to automatize jobs. For example, the machine that we have here, we can buy these extras, but actually we bought the extra of the higher bridge, so we can do more crazy things, like more three-dimensional. We have more margin of working. We didn't bought this. We have the simple one that is, what's this? Something similar to this, that is actually cheap dust collector, doesn't collect as good the dust, but makes the job a little bit to help it keep clean, and it's easy to see through. It happens a lot with this. If you want to cut three-dimensional and you didn't take care that you are going to move, this happens. You crash on the part, and usually this part they usually break faster than the machine. The machine breaks this part. Actually, this one was even worse. This is using a recycled piece of, I think it was a door, and the guy didn't saw there was a screw attached to inside. So they were trying to cut the wood. This is a hard wood. It doesn't look like magnolia. I don't know what kind of wood this, but the mill touched it, took the screw out, broke everything. So it was a mess, like super fast. So always is here the MDev students always like try to use like refurbished pieces of wood or pallets. Be really careful when you use a recycled piece of wood. It might be hidden nails somewhere, and you're gonna break the. Okay, more examples here. For example, this is an architecture model. For example, here you can see there are some areas that they have like a small detail. For example, the holes for the tree. They are different from this one. You can see here that, for example, the cut of this was using a 8mm end mill. We can see the radius here, more or less, and the holes is around 3mm here. So how we do these kind of things? Changing the end mill. Changing the end mill, here is where the party comes. That is, you need to make different toolpaths for the different end mill, and you need to save in different files. This is the same process as you do with the PCB milling, that you do make a file for the 164 and one file for the 132. You cannot send them together because the machine will launch one after each other. Exactly. Unless that depends a lot on the machine configuration. Unless the machine has an automatic tool change, that in that case in the G code we set T1 or T2, and the machine will go and take the tool automatically. And some machines you can make it in the same code, and in the line of code where it says T1, the machine stops, pauses, go to a certain position, pauses, and ask the user, please change the tool. You do it manually, you confirm, and the machine keeps going. But this depends a lot on the configuration of the machine. No, we launch one file, finish, we change the end mill, we make the Z again, and then we launch the next file. It's the same process as the SRMs. We can enable these features, yes, but more automatization means more prone of mistakes if you forget one step. Actually, there is in this machine you can configure a lot of macros, like it's predefined things. For example, for this machine, I have configured auto self-cleaning. That is, we go in the menu, I have a G-code file ready as a macro. That is, when I finish cutting, I take the end mill, I take the collet, I make the Z really low, and the machine will automatically brush all the bed, so I don't need to clean it. Yes, but if you don't make the Z properly, you don't take the end mill out, you don't take the chuck, it will crash the machine on the bed. So you cannot make mistakes when you use automatizations. So we try to use as less as possible, so that doesn't happen. Guys, I need to go 1 second to the restroom. Let's have a 10 minutes break, and let's make a new RhinoCam file, and let's go on to the machine. Okay. Okay, let's keep going a little bit. So remember, let's repeat the whole process so you can actually see it. The first thing we need to choose is that we are using a 3-axis machine. We don't need to define anything else that is a number of axes, that we are using a 3-axis machine. The post processor is quite important. We need to choose the one that is relative to our machine. For example, with RhinoCam, we can produce files for multiple machines. We can even produce for the SRMs 20s, for the Roland. I think I have an old version, so I have a standard Roland that we might try. For example, I remember cutting with SRM with this RhinoCam. So what I did is I just produce a standard one and start trying different post processors. For example, I know the MDX40 is a slightly big version of the SRM20, so it might be also interpreted by the same machine, but might be not. Actually, as far as I remember, I was exporting to the MDX40, but I had to change the first line of the G code manually because the post processor was not exactly the same. Huh? Can you install machines? Yes. Is you go to You go to and you put your post processor in this folder, and basically it's a text file. If you want, we can go and find the post processors. This is all the post processor files for the different type of machine. If you want to add a new machine, you need to go for RhinoCam and look for the post processor for RhinoCam. As for example, for this machine, we didn't have it. I just create my own. I took a generic one. I look at the post processor for this machine of Fusion, and I inherit the parameters.
You show the books.
The both. Yep. Open with. Let's open the post processor. It's still loading. Wait. So, for example, like we have increment, we have NC code. What happened with it? How is the command? G90 is for this. G91 is for that. It's like unroll the whole gcode Instructor builder. For example, notion definition. The post processor will not augment the scale relative to the file. We use a 1-to-1 scale. Some of them they do. Or post processor will output 4 decimals. That depends on your machine definition and what the machine. Some machines they don't like 4 digits. Some machines they like only 2 digits, and if you have 4 digits, they don't read the G code. For example, here. Wait, let's see. Some machines, they don't like the G code like that, assembly. They like it with spaces between the Y and the number. Some machines not. When I say machine, it's the firmware that runs the machine. So it's actually how the base code of the machine is built. Some machines, they also like the G code just in a row line without the spaces.
What cases did you set up the machine?
You don't set up this. You need to know how the firmware of the machine is running.
Okay.
Like you don't make these numbers. No, you can make these numbers. Like I have a RhinoCam post processor building guide. It's 400 pages if you want. I don't even get like 20. I don't know if I have erased it. RhinoCam post processor guide, and each program has its own guide. The post processor decoded. I think this is a PDF. I don't know if it's unloading. What is inside? Like it has some post processor have tool compensation, like already accounting the curve produced by the tool or when they shatter. So in the post processor, there is a lot of things involved. It's first how the movements are created, the tolerances embedded into the machine, the manufacturers. If it's a good manufacturer, the machine has tolerances, and they can account for it in the post processor. So there are a lot of small letters, and they have making a post processor in general is not simple. I took as I don't know, like the guys that sell us the machine didn't give us any post processor. They just given their own software. Like they usually, when you buy a machine like that, they give you a package of you can buy the machine plus firmware, the machine plus firmware plus software, the machine plus firmware plus software plus another software plus another software. The software that they use, they is not the ones that we are used to teach here. Like we have on all the machines, we use RhinoCam because we can use almost all the machines with RhinoCam, for example. We'd like to stay with RhinoCam. We don't want to move to a new software. So in that case, what we did is I spent months trying to find a post processor and I found one for Fusion in a German forum, translating it with Google. I download the post processor. I took a standard NC post processor, like one of the most standard is NC G-code post processor, like it's kind of like all around worker, and I start moving values from one to another one.
Oh, so everything manually.
Yeah, I brought this. Yeah. 3 years ago, I think. I don't even know what is inside right now, to be honest. Depends on the brand. This really depends. For example, Shopbot is some kind of machines that in the lot of labs they use because they are really open. They try to help you with this kind of thing. The support is quite good if you try to do silly things, or so they are helping in this case. For example, CNC step VCN. For example, this is the VCAR Vimicom. It's a post processor for VCAR, and this is the post processor for fusion of this machine. And as far as I understood from the German forum, the guys also build itself, the post processor. So I'm just, this one I made it based on a build of someone built a post processor. So that's why sometimes for post processor, when making some kind of cuts, it fails. When it fails, is the machine doesn't fail. What it does is when you load the file, it says this line, like number 7432, is not compatible. You can acknowledge and still go for it. I might skip the line, might do something weird. So in general, what we do is we go back and get in RhinoCam, change a few settings, like for example, curve interpolation, and that's it. And that line disappears. So when you launch, if you some point you launch a file and the program highlights one line in red, just tell us. Like it might be some things of the post processor not working exactly as it should. Split right, for example, this is the post processor of Fusion on the right, and this is the post processor of RhinoCam. Like the base is already quite different per se. So basically, you need to look for like finder tools. Like, okay, I want to look for, let's see, we have a scale factory parameter here. Let's try to find it in the other one. So I took one like standard template of post processor and started to fill up the numbers. Maybe something is great, maybe something is wrong, maybe not completely, but so far so good. What we do is after writing this processor, we run a lot of tests in the machine, like try to make different shapes, three-dimensional millings, checking accuracy with calipers and measuring the tool on the outcomes to see if the file is exactly as the outcome. We didn't just create the post processor and like hope that it's working. I don't remember right now. Spindle, for example, here we have spindle high value. Some numbers are important. For example, it will set up automatically that if you set up a wrong number in RhinoCam, let's say 50,000, it will automatically constrain to 24,000. Even if you set up a higher number, it will constrain it to the maximum of your machine. In this case, the spindle maximum speed is easy. You can see on the datasheet of the machine when you assemble it. Okay, maximum speed is, you put this number. For example, the spindle low value is 18,000. If you go to the datasheet of the motor, it's not exactly 18,000. 80,000 having the maximum torque. You can go down to 16,000, but you have reduced torque. You have things like that. Miscellaneous definition content, like for example, commands for coolant. If you have cooling, how do you switch it on? How do you switch it off? Some machines, as I said before, they don't like the M7, they like the M5, and it's the same command for the same thing. But some machines they like, some machines they don't. Depends on how they build the machine. And it's quite annoying, actually, boring. Tap clockwise, for example, there are commands for the code to actually make holdings or taps, depends. So remember to choose the process correctly. In this case, we just name it CNC step VCN. The material, the stock. Remember to always do the origin in the top up corner. And the coordinates, as the general in the machines, we can set up. Do I have Paint open? Okay. ¿Por qué? If this is the machine and the origin of the machine is here in this corner, this is the 0, 0 of the machine, absolute 0. You can make it the same as the laser cut. The origin, you can make it here. No? So we set up that this is a new 0. And in the machine, we set up that, okay, this is the start point. This is our 0, 0. It's easy. There are other ways of working. Instead of stating that, what you do is you locate your material on the machine and you measure this distance. That, of course, is a little bit annoying. You need to be really careful. You need to take a ruler and be as accurate as possible. And you can state that this is 2000, for example, or 200, 100. Instead of using relative coordinates, make your own set of relative coordinates. You can set up always to use absolute. And you can set up also this here. Like, what are the corner coordinates? I can set up to be at 200. Joder, ¿qué le pasa? 200, 100. But that is a little bit more confusing in general. It's more prone to make mistakes. That is, for example, if you want to have several cuts of different types of material at once, like you are making a batch of production of different materials you want to have with just one origin and be going to different points relatively. Absolutely. In general, what we do is just set up the origin directly on our material. Because it's easy to see visually. It's difficult to make mistakes because you put the end mill exactly in your end material and you just put this is the origin instead of being measured. What you just need to set up is the size of your material. Let's state a full size material and the thickness. For example, right now we are going to cut. So ideally, now we should go and measure the thickness of the material. Actually, I will bring a small piece of material. Measure. We're going to cut in this leftover for the camera. So let's measure it. It's here, for example, this board is supposed to be 18. This is 17.47. Pause. Don't know if you see in the camera.
For what? 7?
Yes. This 17. Well, depends on 17.53. 1767, 1770, 1732. So more or less I will take 1765 or 1760, 1770. So it's 17.6. Let's take in average, more or less is the higher average of the measures and the size. As we are using a leftover, we will try to be as accurate as possible. So we'll measure always the smaller size, 20 and 87. 20 and 87. Okay, so this is the size of the material we have. This will depend if you locate the material on the X, on the long side, or on the Y side. So let's produce the cut and let's order the parts around it, just like that will be safe. Okay. We know that we're gonna need a rectangle. So I make a rectangle of the same size. Okay, and I'm gonna make an offset of 30 millimeters. Distance 30. So even if I put the screw in the really bad location, I'm still a lot of margin, so I'm not gonna go through any screw. Even so, I'm gonna show you a little trick. For example, let's say we want to put the screw here. How we do that? We're gonna make the ending go and touch 1 millimeter without the material attached. When you have big boards, for example, you are cutting a board, a huge board, you want to have screws on the 4 corners Ideally also like this, because this is 1.2. You want screws each 1.2 meters. So 1.2, 1.2, 1.2, X and Y. But let's say you have a big part, a design like this, like that, and another design that is like that. You want to be sure that this zone doesn't move. And you want to be reassuring, and you want to put more screws. So if you want to put a screw here, how you do it? To find the location where you're not going to hit the screw. Ideally, what you do is you will design your screw in the file. So what you do is you make a point, check that your point is in the Z0, is important, and we will produce an engraving. We will go, before launching our file, we will touch 1 millimeter, and the machine will stop, because it won't be a file just with touches on the material. The machine will stop, we go on the machine, we put the screws in the location, and then we launch the file. So we are sure that is the best way to never touch a screw. Okay, so for example, let's see, here, this piece is going to be loose. So either we can use a tap to fix this piece when we cut, or we can use also a screw and not use tabs. We can fix it with 2 screws. This is going to be a leftover part. We don't care if you have a hole or not. So we can use screws or not. Just for the sake of not putting screws, because I don't have a hand, I will just put tabs. So let's go and let's produce the engraving. Okay, we select the point, machining operations, 2 axes, and we have facing, that is a pocket of the whole surface, pocketing, profiling, going in, on, out of the curve, V-carve roughing. V-carve is when you use, they are not here, okay, but we use special tools like these ones that they are in a V, and basically it's a profiling, but in order to visualize it properly, you need to choose V-carve, because it will show you in the simulation how actually the shape of the V will be on the material. We have V-carving finish cut, engraving, that is what is called considered on cut, and going on the dots. Only engraving works with dots. Then we have like hole pocketing, hole profiling, thread milling, slotting. Like there are a lot of different styles of cutting, but there are small variations of the same. Pocketing and profiling. You can reduce to everything is a pocketing, a profile, but just with more or less settings. For example, a hole profiling is a profiling, but this has some settings that you can tweak to make it slightly better. But making a hole with a profiling is exactly the same if you put good settings. So we go to engraving. We have to find the curve. Okay. We need to choose a tool. We didn't go in on have it. The one that we created yesterday didn't save the file. So let's create the tool. As you can see, there are a lot of types of tools. Like, for example, this one is a lollipop mill. That's nice. Chamfer, flat, thread making, tapered, flat, V-mill, rounded count chamfer. If you have is flat but has a little chamfer on the point. Round ones and flat. We want to have a flat. You can hover and it will say flat end mill. Flat mill, 6 millimeter. We know it's a 6 millimeter end mill. Floater tooth length, holder diameter is 36. Holder length. The important part here is actually the cutting length. Yesterday we were using 1 and the flute length is 27. I remember. This is the number that matters. The diameter and the flute length. Number of flutes, we are using 1 flute. And the fits and speed is where you set up actually the rotation of the motor. Let's go on to 18,000. You remember yesterday the speed what we set up? We could do the chip load calculation. I know that this is Birch plywood is slightly harder than just plywood. For plywood, we use more or less a 5,500. This is birch plywood. Let's use 4,500 or 5,000. Let's go a little bit on the high side. This is how you approach the motion of cutting. We try to use always slightly less than the cutting speed. 4,000, 4,000. And retract is getting out of the material. Let's use the same one. Okay. Be really careful with these numbers. It's really easy to make the mistake of just putting 1 0 more. The machine will try to go to that speed. So be really careful when you put the numbers. We save as new tool. Okay, we select it. And the fits and speeds are already there, inherited. We don't need to touch anything. Clearance plane is the safe area above the material to move. We can choose part mat, stock max, and actually it's almost the same. Part max distance, and we choose like 20. I just like to stay a little bit higher on the safe side. It takes 30 seconds more, but I don't care 30 seconds. Okay, we go to cut parameters. This is how much you want to cut. Location of the cut geometry. From the top, we want to cut down. How much? You can go 3, but in general, you just want to touch. So we can set up 1 or 2. This depends a lot how uneven is your material. This is super flat. We just can grade 1 millimeter is enough. If your wood is badly stored and is bended like this, you will need to put a really high skin clearance so you don't touch your material when moving because it's not touched. And second, you will need to make a big hole so you actually are sure that you are touching, because some areas you might touch and some areas you might not touch. Let's go for 2. And when you set up the total depth, you always need to move the sliders back and forth so they updates the values. And we can make a hole of 2 at once, not a big deal. Entry exit is none. This means vertical movement for both entry and exit. Sorting basically is like save time in the movements, like make a optimized movements to save time. We have 1 point, it's not it can't make any optimization, and we just generate. As you can see, the red line is the movement. This is the engraving. Okay, let's take the pockets. So we're gonna make a cut of 3 millimeter, then 3 millimeter, then we will go through the material. Actually, this is 18 millimeters, so we can choose 5, 5, 5. Okay, let's take the first one. Machine operations, 2-axis, pocketing. We already have selected the region, is this one. Tool, we are using the same tool. The speeds, we check that they are okay. Clearance plane, we check that it's okay. Cut parameters. Here is what matters. You see this tolerance, a stock tolerance, global parameter tolerance. If we have a curve, it will match the curve up to a resolution of 0.1 millimeters, and the other one 0.63. These are really high. Actually, this is the effect values of RhinoCam. I usually try to reduce it to 0.01, 0.1. I think that in pocketing, it tends to don't have that much accuracy by defect RhinoCam. I usually put it 0.1. It's a circle, so let's go a spiral cut. It's going to be smooth and it's not going to make. This is about transitions. If you make a circle and then you make a movement to make the offset and then not a circle, you will make not a smooth movement. A circle, so it's super easy to make a smooth movement just by using a spiral. You will be really constant on X, Y, and Z speeds. It actually doesn't matter a lot which one you use, or don't use the high speed one. It's the only one that you don't need to use. High speed is for machining aluminum or steel. Use a spiral, offset spiral, or offset. Most of the time we use offset spiral. Let's keep with offset spiral. Cut direction, climb or conventional. What wood is this? Birch ply. It's a hard wood, it's a soft wood, it's a medium soft wood. It's a medium to hard, medium. I will say medium. How we know the type of wood that we are using? There's something that is called the Janka test. Janka test is a test that basically they recognize not how hard is the wood by throwing a steel ball. I think I don't remember the weight. And basically forcing it, launching it at certain force and see how much the steel ball has penetrated in the wood. And you can have some charts like this that they tell you the type of wood and how hard is in the Janka test. So height, float emitting controls. So for example, California redwood is a really soft wood. It's around the 500 Janka test. For example, pine, hard pine, yellow birch. So for example, we are around vintage ash, they are soft woods, all these areas. Above 1,500 becomes like medium, up to Bolivian rosewood, up to rosewoods, African rosewood, it becomes already a hardwood. From here to here, everything is hard, and these ones are really, really hard. Ebony is a really, really hard wood. And these ones, they get closer to aluminum on the hardness, on the milling, and they make a really hardness. So it depends a lot on the type of wood you're using. You choose one or the other one. So actually, in your case, we are around the oaks. Pine is slightly higher. Well, we are around here, like 1,200 to 1,800. So more or less, we are in the medium to hard. So let's climb and see actually how it will look like. If it doesn't look really good, we can change a little bit the speeds or change to conventional to give it a second trial. Tool diameter. This is the offset. On the side, on the X and Y, you are making a pocket. You remember that I say that, hey, we are playing at 4,500 to 5,000 RPM speed. I went a little bit higher. So instead of putting 40, that will be a standard movement on the side, I will reduce to 35. I prefer to go a little bit faster, but less movement on the side. It's a little balance. You can always play with this. Cut levels. How much we want to cut, basically. For the first line, we want to cut 5 millimeters. Okay, we update the values. And what is the middle one? It's below 3 step, so 2.5, 2.5. It's easy. Pocket entry, we don't need to touch anything. Advanced cut, we don't need to touch anything. Shorten, we don't need to touch anything. Generate. Okay, 2 steps. Now let's go for the second one. That is going to be go 5 plus 5. So I'm going to change the name, rename 5 millimeter pocket. And let's choose the next one, machine operations. Actually, what we can do is just copy and change the depth, paste. Let's rename it 10 millimeter pocket. Okay. And what we're going to do is erase the vector that we selected, remove active, remove all, and select the GNU curve. That is this one. Enter. Tool is the same, fits are the same. One of the reasons why I'm copying is I don't need to change all the values. I'm going to be using most of the time, most of the values, you don't change the ending. Clearance plane is the same. Cut parameters is the same. Cut levels, here with changes. Picked up. Yesterday, you asked, hey, you already cut 5 millimeters. We can go directly to the 5 millimeter down and start cutting there. No, we have already new one. We have the material and we already make this disappear, no? We don't need to cut again all this area and then keep going on the bottom one. We don't need to do that. We can start directly here, cutting in this area. So we save a little bit of time. You can do that. You need to be careful to don't mismatch the heights. You can mismatch the heights, you will mess up a lot because you can start cutting involuntarily, like really way lower than you might think you are cutting. So in this, if you want to do these strategies, be really careful with the simulation and double check everything. Let's do it. We are not starting on the top. We will pick the top. The top is where? 5, exactly. And the total cut depth? No, it's 5. Flap 5 plus 5. You are cutting 5 over 5. You see, that's why it's really easy to mess up. And actually, this depends a lot on the software you use. For example, Aspire works completely different. You set up the total, as you were saying, you set up 10, but you choose where you start. So it depends a lot on which software you use. You need to be careful on how it interprets these numbers. Let's check it. I will generate and see the simulation. Huh. It is. It's negative. We need to set up a negative number. That's why it's important to check the simulations. So let's recalculate again and set up -5. Generate. You see, suddenly it changed from cutting in the air to cutting really low. Let's review that is actually cutting well. Yes, it's not cutting in the zones that we already cut it in the first pocket. That is this one. You're adding on the bottom of that one. It's really important to be really careful with these settings when you try to save time. It might save you like, it's gonna save 1 minute of cutting because it's one circle. When you have a full board full of circles, it's maybe 1 or 2 hours of cutting. But at the same time, you can mess up everything really easily. Actually, you will see on the machine bed that there are some holes, like the bed of the machine should be a scratch. Some lines are like 2 centimeters depth because they have messed up with these kind of things. Okay, let's take the last one. Oh, chat. Because things on material is 10. There is some sort of Bible for materials.
Sorry, the second message was a while ago, but it passed. And I think, yeah, you were talking about the first cut and the second cut, how deep it should be. So that's fine. But for the material, is there like, if someone, because I'm not very, I'm learning with as you go on about the material, the same way there's like a Bible for endments, let's say. Is there some sort of reference book for wood, another one for metal, so that we know we know a little bit more about the materials we're using?
You mean for milling or in general?
In general, in Thailand.
Oof, not that I know.
Okay. Recommendation.
One good tip is always look at the density of the material. Usually, like higher density materials, they are hard. Like it's just look at the mole density of the materials.
Okay. Merci.
Yeah. Okay, we're closing the door. So now let's copy this toolpath. Let's paste it again, and now this is going to be the rename it. It's going to be the 50 millimeters, for example, or we can just say like 50 millimeters. The wood was 18, no? Yeah. 18. Let's go. Let's put, and in this case, I will put through to be that I'm going to eat all the material. So it's going to be the one that destroys all the material left. As I don't remember the size, I will check it. 17.6. Okay. Let's erase this one, remove all, select the new curve, this one, enter, perfect. The tool, okay there, we don't need to change anything. Cut parameters, we don't need to touch anything. Okay, pick the top. We just went from where to where. That's one of the reasons why I'm putting the names. So I remember, I don't need to go inside the files. So we are taking from -10, total cut depth, the material is 17.6. We want to be sure that we are cutting enough. So let's go to 18. 18 minus 10 is 8. We need to be really careful with these things. and we move the slider. For example, we can choose between 3.2 and 2.4. It's a hard boot, usually doesn't like to cut too much in the depth. This kind of, we are using a down cutter end mill, doesn't like to cut deep. So let's go to the safe side, 2.4. Might take a little bit more, but not a big deal. Okay, entry, we don't change, sorting, generate. Let's check again that this is okay. Completely logical, seems so far so good. Okay, and now let's jump onto this, that is the in-cut. We're gonna separate this part out. Okay, so we can select the file now, or we can do it later. We can machine operation, 2D access, profiling. We select the curve, enter. Tool, we have the tool selected. We check the speed and speeds, perfect. Clearance plane, perfect. Cut parameters, the tolerance by default is okay. By default, RhinoCam uses a mix. It goes climb and conventional to save time. Let's choose climb. We want to cut where? Inside. Cut levels. How much we want to cut? 18. We're going to use a down cutter end mill. Down cutter end mill, as we are pushing the material down, is moving a little bit the Z. So we want to be sure that we are cutting completely through. So I might increase like 0.2 millimeters. Like, so it's 18.2. First, cleaner surface on the top, and exactly this. In this case, the wood. This is a good wood. The layers are thin. It's easy to chip them out, the edges, and it will get worse result on the back. But the back is pressed against the material, the bed of the machine, so it's not chipping that much. There's lower in general, like for plywoods, if they work really well, we don't need to fix as strongly as the up cutter because it's not tending to move the material down. I really like, personally, I really love down cutters and straight cutters. Like they are really easy to use, like easier to use, less sensible to mistakes. They are worse. They are not as fast, yes, but they work really well and they give really clean cuts in general. But downside, price of the cutters, like it's almost double of our up cutter in general, and you cannot make faults. That is a huge. And you say, hey, we are engraving a touch, yeah, 2 millimeter touch. It's not going to compress. That's one of the settings we set up here. It enters in a ramp. Exactly. So we update the values and we will take steps of, you see, this is not really, there's a big change between both. Manually, yes, but that will make the steps as you want, and the last one, it will accommodate more or less. So something that ideally, let's just, is this a male hard wood? So let's stay with 1.8. I will go to the safe side always. Entry exit. This is the entry vertical movement. None enters vertical on the path. Along path, it will make a ramp, a little ramp to enter. So always state this one. And exit vertical also. Advanced cut parameters, we don't need to say anything. Sorting, we don't need to say anything. What we forgot? This piece is going to be free. We want to have a tab, at least 1 or 2 tabs. So in advanced cut parameters, you can say rectangular tabs. This is a small part, so with just 2 tabs should be enough. Of 2 by 2. Generate. And we can see the tab is here, not a bad location. And here is not a bad location. And it's making the little ramps of entry. Good. So far, so good.
I mean, the previous one as well, and
This one, we are destroying all the material.
Okay.
So there will not be leftover material. So now it's time to do the outcuts. The outcuts of this is going to be the same as this one, that is in cut 18.2. This is my personal workflow. I always state the type of cutting and the depth of cut. So I completely sure that how deep I'm going. We copy. I'm going to rename it outcut 18.2. Okay, and let's remove all the lines and select the new ones. Tick, tick, tick. Okay. Tool selected, speeds are selected, clearance planes is the same, cut parameters are the same. In this case, outside, not exactly the same. The difference between one cut and the other one is one we are cutting inside the vector, another one is outside the vector. Cut levels is the same. Cut levels, we are cutting the same depth. Entry, exit, the same. Tabs, also the same. Sorting up. In this case, we can say minimum distance if 3 vectors is not to make any huge change. Generate, and you can see that first it will go this one, finish, move in the air, go this one, then move this one. The tabs are exactly one in front of each other, so it's a perfect location. So now that we have set up everything, let's first, for example, check the time information. It's going to take 12 minutes, 0.71. More or less, it's not 12, it's going to be 17, 15, more or less. Let's simulate this. We select it, simulate. We can, it doesn't appear, just make it bigger, simulate, and play. Nothing to simulate. Let's select everything. Play. Right now it's in high. In 2D simulation, this goes quite fast. In 3-dimensional simulation, this is awfully slow to calculate. Depends on the simulation, but if you are making a really complex 3-dimensional mill, this can take half an hour to calculate the simulation. Even sometimes more than the milling time. Okay, everything seems so far so good. The tabs are still in place. We have enough part here. We have made the little touch here for putting the screw. Okay, the file seems okay. How to save this? You can select to save in packs. This is one toolpath, this is another toolpath, this is another toolpath, this is another toolpath, this is another toolpath. Let's save the engraving separately because we want the machine to stop after setting up the screw. We just post it and it's going to be screw location. Enter. You see, super long G-code. And we select the other ones, post, and this is my first file. Okay. So now that we have saved this, let's use the cloud to move the files to the machine computer. File station, have students, staff, edu, and I will just throw it here in the middle. Screws, okay, and my first file. Okay, now that we are ready, we can go to the machine. Let's go.